Maintenance. Inside the quiet maintenance hangar, the African-American male engineer and female engineer stand observing the narrow-body aircraft.
From the outside, the modern aircraft always creates a calm and stable feeling to the point that passengers almost forget it is carrying hundreds of people through the sky.
That feeling of stability makes many people believe aircraft safety simply comes from stronger engines or more advanced material.
The energy readings are stabilizing across the main conduits. Check the flow rate on auxiliary systems. A modern aircraft never places its trust in only one single system.
Workers aged 22 to 25 continue inspecting every wiring compartment, every control module, and every protective material layer.
The central question begins to emerge more clearly inside the quiet maintenance hangar, as everyone realizes that what makes modern aircraft safe is not one special device. If one layer of protection fails, what happens next inside an aircraft flying high above the ground where there is no opportunity to stop and repair like on land?
That is why the entire aviation industry has built modern aircraft as systems constantly prepared for the possibility of failure, instead of simply hoping failure will never happen. During normal operation, every system inside the narrow-body aircraft with matte gray metallic surface, no logos, no markings.
Sensors inside the engines continuously send data to the central computer, while the navigation system also compares its own information to detect abnormalities as early as possible.
Aircraft stability does not come from silence, but from systems constantly checking one another.
Check the insulation on that main bundle. It looks slightly chafed near the connector. I see it. Let's have them run a TDR on that section before we sign off.
Every flight control system has its own backup power source, and even those backup systems have additional layers of support.
Decisions. Inside the cockpit, pilots often see multiple identical displays, not because of redundancy alone, but because modern aircraft, if one sensor produces abnormal data, the aircraft will not immediately trust it, but instead compare it with other sources before reacting. Sorts. These protective layers operate so silently that most passengers will never realize that beneath every smooth flight,
True aviation safety lies in detecting failure before failure becomes disaster.
Under normal conditions, every system inside a modern aircraft is designed with the assumption that any component may eventually experience problems at some point in the future.
But that assumption also creates a major contradiction when people begin asking why the aviation industry keeps adding increasingly.
The greatest danger in aviation is not a single failure, but a chain of failures occurring simultaneously. One faulty sensor may not be dangerous alone, but if the verification system also fails at the same time.
The female engineer aged 22 to 25 opens historical inspection data and points out that many aviation accidents did not be.
Workers aged 22 to 25 continue replacing components even before waiting complete failure.
The core contradiction becomes clearer as aircraft grow more advanced, because the number of systems requiring protection also increases.
A new protective layer can sometimes create new risks if it cannot coordinate precisely with the other layers inside the enormous technical structure.
The greatest challenge is not creating more systems, but ensuring every system understands and responds to each other at the correct moment. The female engineer aged 22 to 25 silently watches fluctuating data streams on the screen and realizes that The core reason modern aircraft require multiple layers of protection is that the flight environment does not allow humans time to correct mistakes the way they can on the ground.
Annealings. When an aircraft is flying tens of thousands of feet above the ground, every decision must be made almost instantly.
That is why the aviation industry built its safety philosophy around the principle that no single system is ever allowed to become the sole point of failure for an entire flight.
If one power source fails, another source immediately takes over, before the pilots even realize the transition is happening.
Even flight control software is designed with multiple verification layers to prevent one incorrect command from spreading across the entire system.
Right, understood. Make sure the quilting is properly seated around the hydraulic lines. The thermal protection is secured.
One physical protection layer prevents damage from spreading, while electronic protection warns and operational protection.
These layers of protection do not operate independently, but continuously support each other, like multiple security rings protecting one.
Modern aircraft are not designed based on the belief that everything will remain perfect, but on the belief that every mistake must be stopped before it spreads.
Every protection layer exists not because the system is weak, but because aviation fully understands the limitations of every technology. Conclusions. That is why modern aircraft always contain multiple overlapping layers of protection, because in aviation, safety is not
Healthiest.
Compared with many other vehicles, modern aircraft are different because they are not only designed to function properly,
but to. A car can stop on the roadside when something fails, but an aircraft in the middle of the sky must continue maintaining control throughout the flight until it lands safely. This unique operating environment forced the aviation industry to develop more protective layers than any other form of civilian transportation.
every layer of protection inside an aircraft is like another silent supervisor watching the same mission.
Workers aged 22 to 25 continue completing final inspection procedures inside the clean and quiet environment.
Message links. A single system may be powerful, but only multiple protective layers working together correctly create the
most important protection layer sometimes lies not in technology, but in designing preventive thinking from the very beginning.
Werther. The South Asian female engineer aged 22 to 25 nods while watching the stable data streams because she
understands. Physical protection, electronic systems, software verification, and operational procedures ultimately meet at one shared objective.
That transforms modern aircraft into more transportation machines.
Data check complete on Section 4. Have the ground crew secure the panels.
Acknowledged. Stability is holding steady across the board.
Cross-reference the hydraulic levels here. Levels confirmed and logged. Section 472 verified.
The question of why modern aircraft require multiple layers of protection is finally answered clearly when everyone understands that
every protection layer exists in preparation for the possibility that another layer may fail, and that philosophy has transformed. True safety is not eliminating all risk, but preventing risk from ever becoming disaster.
Every protective layer inside the aircraft begins with one deeply human truth: accepting that mistakes can always happen. The narrow-body aircraft with matte gray metallic surface, no logos, no markings, continues resting in
islands. And that is why modern aircraft can carry people across the sky every day, not because they are perfectly flawless, but storied. Inside the silence of every modern flight, there is always an entire hidden world of engineering, quietly